And finally, we have gotten to what is probably the most famous physics equation, besides E equals mc squared, and that is Newton's second law. So Newton's second law is essentially just the equation here. Let's go over it together. But before that, learning objective is I can use Newton's second law to model... Before we start that, let's go over the learning objective. The learning objective is that I can use Newton's second law to mathematically model and predict the motion of an object based on forces. The idea is that you're going to use Newton's second law to make predictions about the motion of an object. So right here, we have Newton's second law, and this is stating that the sum of all forces in a direction, remember we're going to do this one direction at a time, is equal to mass times acceleration. In the previous lesson, we learned that about Newton's first law, and the idea that if acceleration was zero, net force must be zero. And this shows why that's the case. If we suddenly make acceleration equal to zero, then that means that this whole right side of the equation would equal zero, and therefore the sum of all forces would equal zero. The net external force in a direction is equal to the mass times the object's... The net external force in a direction is equal to the mass of the object times its acceleration in that direction. And I want to be very specific about that. This mass is in regards to the object that is accelerating. And the sum of all forces is in regard to the object that is experiencing those forces. You got to keep track of what object you're talking about. Sometimes when students apply the Newton's second law, they'll use forces acting on one object to describe the motion of a different object, or use the wrong mass, or not know what mass they're talking about. Right now, we're only going to have really one object that is very obvious. But in future learning objectives, there's going to be multiple masses, and you got to understand what mass is the one that's being multiplied by acceleration. It's the object that is moving, or the object that we care about, the object that's part of the system, and it's the object that these forces that you're applying on the left side are being applied on. Let's look at some examples of applying Newton's first. Let's look at some examples of applying Newton's second law. So here we have a person pushing a box, and on this left case, the box is on a skateboard that we assume is perfectly frictionless. So the idea is that there is no friction acting in the opposite direction of the motion. So let's write out Newton's second law. And there's a joke that every physics problem starts with Newton's second law, and it's a joke for a reason. Jokes are based on truth, and it is true. So let's write out the sum of all forces. Let's make my sigma look better. There we go. Sum of all forces is equal to mass times acceleration. It would be best to write in that this is specifically in the x direction. However, we understand that this entire problem is going to be one-dimensional. So we can drop this sub-notation here. We can drop the subscripts and just talk about sum of all forces equals mass times acceleration. So the object that we're considering, and that's something you got to think about. The object we're considering is the box. We have its mass, and we have one force that's being applied on it. And there's only one force. So when you have a case of only one force, that's also the net force. So let's break out this sigma f. And this is a very important step. You got to do this every time. You take this sigma f, the sum of all forces, and you write each individual force. So we don't have a name for this, so I guess it's the applied force. So we're just going to go straight to the units, straight to the numbers. So this is 200 newtons. One thing we also haven't done in the problem that we probably should is we need to declare a direction as being positive. So we're going to say to the right is positive. Everything's acting to the right, so it just makes sense to use that as positive. So the sum of all forces equals 200, but it also equals whatever the mass times the acceleration is. So the mass is 50 kilograms times the acceleration. So in this problem, we only have one unknown. So although I didn't write the problem question, we can be pretty assured that we're going to be solving for acceleration here. In order to solve for acceleration, we're going to divide both sides by 50 kilograms to cancel it on the right side. So we're going to divide both sides by 50 kilograms. 200 divided by 50 is 4. Now let's talk about the units. A newton isn't just a newton. A newton is a kilogram meter divided by seconds squared. Kilogram meter divided by second squared. And what we're doing is we're dividing it by a kilogram. That's going to equal 4. And then all we're going to do is just cancel out those kilograms. So we get meters per second squared, which is exactly the units we were looking for because we were solving for acceleration. Before we go on to the next problem, I want to talk again about the units of a newton. Previously, I said that the units of a newton were equal to a kilogram times a meter per second squared. And I color-coded out the kilogram and the meter per second squared. It should be obvious now why that's the case. A kilogram is a unit of mass, and a meter per second squared is a unit of acceleration. So the units themselves kind of tell you what the equation for force would be. The sum of all forces must equal mass times acceleration because in the units, we have a unit of mass times a unit of acceleration. All right, returning to the problems, the practice problems, the examples. We're going to take a look at an example where now we have a frictional force. So we have an applied force and a frictional force. We have two forces. They're acting in opposite directions, so it's really important that we designate one side to be positive and the other direction to be negative. So we're going to go ahead and apply right is positive, left is negative. That is generally the convention. Let's start every physics problem, or almost every physics problem, with writing Newton's second law. Sum of all forces equals mass times acceleration. Next, what we're going to do is we're going to break this sigma out into what it is made of. So sigma, again, means sum of all, so we're going to add up all the forces. Here's what we're going to do. We're going to label this FA, so force applied, and then generally, friction gets a lowercase f. That's usually the convention for friction is lowercase f. So let's start with the applied force. We're going to go force A, and it's in the positive direction, so it's going to be positive, but we can just have nothing in front of it to signify positive. And then we're going to subtract the force of friction. So here we're using the strategy of we're going to plug in the number without any negatives because we've already accounted for the negative by subtracting the force. This force is going in the opposite direction. It's going in the negative direction. So we're going to subtract the force. And we're not going to put in a negative because if we put in a negative, we're going to have two negatives cancel each other. And then all of a sudden the frictional force would be adding to the applied force. That wouldn't make sense. That would make it go even faster. But friction can't make it go faster. It has to make it go slower. So now, the sum of all forces equals the applied force minus the frictional force. And that equals mass times acceleration. Again, here we're solving for the acceleration. So we're going to divide both sides by mass. So it cancels on the right side, and let's move it to the left side. So overall, we have acceleration is equal to the force applied minus the frictional force divided by mass. Let's plug in some numbers, and then let's analyze our solution. So the applied force is 300 newtons. The frictional force is 178 newtons. And then the mass was 50 kilograms. After plugging that in the calculator, what we get is 2.44, and we already have talked about what the units are going to be. They're going to be meters per second squared, should be because it's an acceleration. And that would be the answer. But let's take a look at this equation that we have found here. By solving for acceleration, we came up with an expression. So let me just move that over here and write it a bit bigger. Force applied minus the force of friction divided by the mass. And what we like to do is, in physics, is look at different cases. How would the value of acceleration change if we changed one of the values or the other value? So what would happen if the force applied increased, but nothing else changed? Well then, acceleration would also increase. Makes sense. We're pushing harder. Okay. Let's try another case. So what would happen if the frictional force increases? Well, if the frictional force increases, that means that the box is being slowed down even more. Just from our own mental idea, if we had larger friction, it's going to slow down faster. Or in this case, since the acceleration was to the right, it's not going to accelerate as fast. If frictional force goes up, then the value of acceleration should go down because we're subtracting the frictional force. Now, what would happen if the frictional force was greater than the force applied? Well, then in that case, acceleration would be negative. What would that be? Well, that would be the case where the box is slowing down now, where the person isn't pushing as hard on the box as friction is pushing back on it. And let's ask another last question. What would happen if the mass of the box increased for some reason? Well, since mass is in the denominator, that means acceleration must go down. So a heavier box is harder to accelerate than a lighter box. A heavier box would take more force to accelerate to the same speed as a lighter box would. In both of the previous examples, we've been solving for acceleration. In this example, what we're going to do is we're actually going to be solving for a force. And we know what the acceleration is. Luckily, we already have the free body diagram drawn. If the free body diagram was not there, we should draw it. So now, after drawing the free body diagram, we should write out Newton's second law. It's one of the very first steps every time after drawing it. Write out Newton's second law. Sum of all forces equals mass times acceleration. And again, what we're going to do is we're going to break the sum of all forces into, in this case, the three forces that are acting on this object, acting on this box. Another step we haven't done yet, but we should do, is declare what direction is positive. We're going to go with the convention of to the right is positive. So let's start with force 1. I like to start with the positive force, because if you start with a negative force, you have to put a negative in front of it. We'll start with the positive force, force 1. And then the other two forces are going in the opposite direction, so we're going to write minus F2 minus F3. And that equals the mass of the object times its acceleration. Before we continue, let's just take a look at the acceleration. The acceleration here is negative. A negative acceleration would mean that the acceleration is to the left. But a negative acceleration would mean that the net force is also to the left. So we know that F2 plus F3 must be greater than F1. The forces going to the left added together must be greater than the force going to the right, or else acceleration would be towards the right. Well, let's continue this. So again, we're solving for force 3 in this case. So what we need to do is we need to get force 3 all by itself. One way I would like to do that is I'm going to take force 3 and move it to the other side, and then take mass times acceleration and move it to where force 3 is. How we can do that is we can add force 3 to both sides. So we're going to add force 3 to both sides, and we're going to subtract mass times acceleration on both sides. Got a little messy there, but on both sides, what we're doing is adding force 3 and subtracting mass times acceleration. That's just going to flip-flop the positions of F3 and mass times acceleration. So what we're going to get is force 1 minus force 2 minus mass times acceleration equals force 3. The reason I wanted to move force 3 to the other side and not like force 1 and force 2 is force 3 was already negative. And by moving the negatives to the other side, we're going to be making them positive. And typically you want the answer you're solving for in the end to be positive. The value can be negative, but the variable should be positive. It shouldn't have a negative applied to it. All right, now I'm going to take this equation, move it over here. I'm running out of room. We're going to write F3, so I'm just going to flip the equation around. F3 is equal to F1 minus F2 minus MA, but since we've isolated the variable we're solving for, we can now just go straight to solving it. It's like plugging in numbers. So let's go ahead and do that. F1, 200 newtons. F2 is, we're going to subtract F2, which is 125 newtons. And then we're going to subtract MA. So the mass is 10 kilograms. And that's going to be multiplied by the acceleration, which in this case, we need to plug in the negative in there as well. Negative 100 or 1.25 meters per second squared. Because we didn't apply a negative in the beginning. Since we didn't apply that negative in the beginning, we're relying on the number that we plug in to include the sign. So acceleration is negative in this case, because that's the value we were given. Again, we can plug in a positive value for acceleration if we had included the negative outside, like in front of it, from the very beginning. But we did not. So we got to include the sign now, which is negative. A negative times a negative is going to get us a positive. So we're going to have 12.5. Kilogram times meter per second squared is just a newton. So we have 200 newtons minus 125 newtons is going to give us 75 newtons. So we have 75 newtons plus, because we had two negatives here, plus 12.5 newtons. And that's going to equal our force 3. Using some quick mental math, that's going to be 87.5. So 87.5 newtons is force 3. And we can just bucks our answer right there. The students looking at this note without watching the video are going to be very lost in all of this algebra and arrows going around. All right, I've shown you 3 example problems of increasing difficulty. Now is your time to practice. So first practice problem, you're going to create your own physics problem. It's a really useful skill to be able to create your own test problems. You're going to include 3 or more forces, have an object accelerating, and that object's acceleration should be 3 meters per second squared. You can choose the other forces such that you get that 3 meters per second squared. And none of the forces can be 0. The second problem is a ball is accelerating at 3.5 meters per second. It's another way of saying meters per second squared. The ball is subject to 2 forces. One is 300 newtons and the other is 20 newtons. What is the mass of the ball? So this time, you're trying to find out what the mass of the ball is, not the acceleration or the missing force.